we start homework 2 and get on the board and start deriving a few equations, I wanted to go over the variables that are given, as there's a lot to write down, and so I want to make sure that I don't miss anything while going over it. And I'll write out and kind of show the problem that we're going to be doing, or homework C right here, on the board, but these variables are important as they give a lot of information on the different types of units or what they're looking for. And so you can think of it as what we're solving is for a tank with a cooling jacket that is around it, all right? And the outlet for that tank is at the top, so the volume remains constant. And we also have an inlet flow, and we have a few things we want to calculate. And so in this problem, or let's see if I can make that bigger. No, that just searches it. It says to illustrate how the constantly stirring reactor, so it's going to, all that means is that it's equally distributed, and it's going to be always continuously stirring. Can exhibit a nonlinear dynamic behavior. We simulate the effect of a step change in the coolant temperature Tc. And so again, all that is given, and that's given down here. Actually, no, as what Tc is actually what we're going to be changing, and we're going to be seeing what that change in the coolant temperature, how that affects the different codes that we actually, the different equations that we've are going to derive. And then it also says, it gives a few different values down here. It talks about how it's an exothermic first order. Yeah, exothermic irreversible first order. It means it can't go from B to A. It can only go from A to B. And it's exothermic, which is why we have delta H down here, or negative delta H, and it gives us how much joules are released per mole that is reacted. The two-state variables of the OD of the differential equations are the concentration of A, so Ca, and the reactor temperature. So that these are the two things that are going to be changing. All right. Reactor temperature, and these are manipulated by Tc. So the temperature that Tc is at will change the reactor temperature along with the concentration of A. And these are simulated, and then under here is these two cases are simulated based on the cooling changes. This is for the coding aspect. But what this is telling us is that we need to create two different equations. One for the, let's see, it says, where is that? One for the concentration and the other for the reactor temperature. And so those are what we're going to be going over. And so let's go over our variables now. So Q, our rate, is 100 liters per minute, which this means because there's only one Q and there's nothing about the rate changing here, that Q is constant. Our initial, so from our inlet stream, our concentration is 1 mole per liter, along with our temperature of that initial stream being 350 Kelvin. Our volume is constant at 100 liters, which again is very important. And so is our density at 1,000 grams per liter. The C, or the specific heat, is 0.239 joules per grams Kelvin. So we already know we're going to be dealing in Kelvin, but now this gives us that we're going to be dealing with grams as well. And the heat that delta H, negative delta H, or our exotherm that is released from this reaction is 5 times 10 to the 4th joules per mole. So 50,000 joules per mole. Parameter E over R is a part of the rate reaction, which will be shown up on the board shortly, along with K naught, which is another thing that goes into that reaction, or into that formula. UA is a very advanced type of reaction formula that states a few things. It really takes into effect the different, if it's a first order or not, the type of geometry your tank is in. It's really a ends-all catch-all coefficient, and it's also a part of that equation that will be up on the board shortly. It also gives us a few initial conditions, which will be really useful as we need to find T naught and then how that's going to change. And so now I'm going to go and write down most of these variables, or I'll take out a few, like the T naught, CA0, T0, if they're needed or not. That way I'll have some room on the board to actually work this out. So now that I have all of the variables written out on the board, even though it's hard to see, I'm going to draw what we're trying to solve for, or our situation I'll draw. So we have a tank. We have a tank that's being insulated, and we'll pretend that's the same height. We have a tank that's being insulated, and all right, it's being insulated. And because this is a continuously stirred tank reactor, it means we've got one of these things in here, which is just kind of like a mixer. It's just going like keeping the density constant and all of the above. And also, we're going to pretend what I drew is accurately correct, and that right here is the outflow. It's a top outflow, and so what that means is that the volume can't get higher than that because it'll spill out. And so this is how the volume remains constant in this type of reaction, or this type of reactor. We also have an inlet flow. Our inlet flow is also known as Q, as the rate. It has a temperature initial, and it has a concentration initial. So the concentration that's coming in remains constant around 1 mole per liter, and so does the rate. The temperature remains constant as well. And what we want to calculate is how the change in this temperature affects the concentration of the tank, along with how it affects the temperature of the tank. And so let's start off with calculating the amount of concentration, or the mass. And so we want to do a mass balance of this reaction. And so to do a mass balance, first we got to write on one side. So it's going to be the differential of, we want moles per minute, right? So it's over dt. So we want moles. We have Q, which is liters per minute, and we have CAI, which is, well, let's go through these. We've got, so if we want moles per minute, it's already over dt, so we just want to get moles. And so CAI is also known as moles per liter, and Q, not CI, Q, CI, moles per liter, and volume is just liters. And so that would get us just moles. So it's going to be CAI times V. And that's going to equal, and this also sets the standard actually, it's before this is moles per minute. We need to know how much is coming in. And so we have Q, which is 100 liters per minute, so Qn, which is in liters per minute. And we have CAI, which is in moles per liter. That would cancel out and give us moles per minute, which is what we want. So we're going to do Qn times CAI. All right? And that's what's coming in. And what's going to be going out is going to be, the rate that is coming out is going to be Q. Because, well, we can just, let's put this as Q out for now. So it's going to be Q out multiplied by the concentration of the tanks. And we're going to call that CA, as that's what we're trying to calculate the change of. And another thing that we know, or sorry, I'm getting ahead of myself, what also is happening is that there's going to be some taking out. There's going to be A that is taken out because of this reaction. And before I get ahead of myself, let me get back to what these equations I have written right here. So what, it's hard to tell, I know on the screen. So we have K equals K naught times e to the power of negative ER times 1 over T. And what this helps us calculate, it calculates K. And K multiplied by the concentration of A gives us the rate at which A is being consumed. It gives us that in moles per liter per minute, which means that our reactor, or the rate that our that A is being consumed, is on a volumetric basis. It's also, it needs the bigger volume. Sorry, I'm getting ahead of myself again. Stumbling over my words. that it depends on volume. So the size of the reactor is dependent, the rate at which A is being consumed is dependent on the volume of the tank, okay? And we want to know how much is being consumed, which we need to get this in moles per meter, or moles per minute. And so we have K times Ca, so we're going to subtract again, as we're going to be taking it out of this tank, as it's turning into something else, turning into B. So it's going to be K times Ca, which gives us moles per liter per minute, which we want moles per minute. And so to get it out of liters, we have to multiply by volume, so the liters will cancel out, times volume. And another big thing is that Q in equals Q out, because if the volume is constant and it's never going to change, well then how will the rate in exceed or be less than the rate out? If it increases, the rate out is going to increase because it's going to be reaching that top tipping point faster. If it decreases, it's going to be slowing it down, the rate at which it spills out of that hole or over the side. And so we can write Q in equals Q out. All right, and another thing that we know is that the volume remains constant, which means we can take it out of this differential. And so we could have, let's see, maybe QCAI minus QCA, and we're going to multiply that, divide that by the volume, minus K times Ca, as that's already multiplied by volume, and that equals dCA. Oh, another thing, I put dCAI here. Well, we already know the initial concentration as it's actually given to us right here. And so that actually what we're calculating is dCA, or the change in the volume in the tank. And now we're going to be getting rid of volume, as I said earlier. So it's going to be dCA over dt, or the concentration of moles divided by minutes. And this is important, but this is the mass balance equation. So we have dCA, or the change in the concentration of A, equals Q times CAI, or the initial, minus Q times Ca over volume, minus K times Ca, or the concentration in the tank. And all right, because as we stated earlier, that the rate at which A is being converted to B is volume dependent. And so when we divide across by volume, we can get rid of that. And so it just talks about just states that the rate in minus the rate out, multiplied by the concentrations of each, divided by the volume. Now we subtract the rate at which A is being consumed, and that gives us the change, in how much concentration of A there is in the tank at this time, or at any time, theoretically. Now that we've calculated the equation, or the differential equation, for the mass leaving or entering the system, or the change in mass, now we get to do the same thing with the energy of the system. Or how we're going to use it is, how we're going to be using it is joules per minute. Yeah, joules per minute. But before we get to do that, we need to incorporate what UA, or at least explain what UA is. So UA times T minus TC, this calculates the amount of heat that is going to be leaving our system because of this cooling jacket. So I'm going to be writing over here just heat loss. Heat or energy loss would be acceptable. And again, this is what's going to be subtracting or taking this heat, or absorbing this heat that this exothermic reaction takes or produces, and it's what keeps this from being a runaway reaction. And so now we get to calculate the energy balance. So on one side, we want to calculate this in joules per minute. So to get in joules per minute, we've got a lot of different things we're going to have to multiply by. And so first, let's find something that actually has joules. And so we're going to use C. And so we have C, or let me write d over dt. So C is in joules per gram Kelvin. And so now we have C. Now when we have to multiply by something to either cancel grams or kilograms. Let's multiply by density, as this will get rid of the grams but give us a liter. So grams over liter. So now we have rho. What's next? Now we have Kelvin. So now we get to multiply by temperature. And the one last thing is the volume, as what we have right now is liters. We have joules over liters. So if we multiply by volume, this gives us the joules per minute, or what we want. So now, let's calculate the amount of, what should we calculate first? Let's calculate the joules that are released from this exothermic reaction. So we have negative HR. So that is 5e to the 4th joules per mole. So we have, I'm not going to write down the amount, I'm just going to write down the variable, excuse me. So I'm just going to write HR, which is in joules per mole. So now we want to get rid of mole and also incorporate minutes. And to do that, if you notice over here in RA, it's in moles per liter per minute. And so if we multiply by K times Ca, which is the same thing, you'll notice that we get, so this is mole per liter minute. So we have moles cancels, and we want minutes. So the only thing left we have is liters. And so, like before, we have to multiply by volume. We also have to incorporate the temperature that is coming in from the tank. And so that would be, we have to do Ti Yeah, because we want to talk about the rate at which our energy is coming in. So we're going to add the rate. So first let's talk about Ti, as that's going to be in Kelvin. And well, we want joules per mole, joules per minute. So let's do rate, as this is what's going to be coming in. So we have Q, which is liters per minute. And so that means we already have minutes. So now we need to try and get from liters all the way to joules. And so now we have liters. What can we divide by that has liters in it? Well, one of the only things over here that has liters in the denominator is going to be the density. So we're going to multiply by density, which gives us grams per liter. So now we have grams per minute, and we're almost doing the exact same thing as what we started with over here. And so now that we have grams per minute, what can we do to get rid of grams? So that's going to be C, or joules per gram Kelvin. So C, which is joules per gram Kelvin. And so now we need to multiply this by the temperature, which is in Kelvin, and that leaves us with joules per minute. And one thing we can do, I'm going to do it on the next step, is we can bring this and subtract everything by this, by our UAT minus TC, as that's what's going to be taking energy from the system. And now that we have, actually I'll write that down here. So minus UA, then T minus TC. Now, we have to figure out which of these are constants. And so we know the volume is constant, so we're going to take that out. We know that density is constant, we're going to take that out. And we know that C is constant, so we're going to take that out. So we're going to end up having dt over dt, or d temperature over minutes. So we're going to have Kelvin minutes eventually, but we don't really care about that, as we already have our definitive minute or definitive unit as joules per minute. And so now we're going to divide everything by C, rho, and V. So in this first block, we have HR, or we're going to call this negative HR, as it's already negative over there, negative HR times K times CA times V. And so V is going to cancel, so we're going to divide this entire thing by C times rho. The next bit has rho in it. Okay, we're good there. It has C in it, and so we're good there. So we have rho and C, so it's going to be plus Q T over C. Okay, C cancels and rho cancels, and the only other thing we're dividing by is volume. So, how did I get rid of liters over here? Oh, I started with liters. Okay, so over volume. And then we're going to subtract by UA T minus TC divided by CPV. And this, what we have here, should theoretically be the differential equation that calculates the change in energy of our system. While looking through this, I realized I messed up and didn't shore my bets, or I messed up a little bit while trying to explain something and also deriving it. And so what I have over here is T. I have Q rho C multiplied by T. Well, this T actually represents the change from temperature of the incoming rate, as again, this is in joules per minute, so the rate that this is coming in, minus the temperature of the coolant. As without this rate, the entire temperature of the tank would be the temperature of this coolant. And so the temperature that I have here should be Ti minus Tc. And so we can rectify that real quick. So we have Ti minus Tc. And so our entire equation is d temperature, or dt, over dt equals negative HR times K times Ca all over Cp plus Q over V multiplied by Ti minus Tc subtracted, which is another way of saying it's taking out of heat now, UA times multiplied by the temperature of the tank minus the temperature of the coolant divided by C, P, and V. And what this is stating is that what we derived is in joules per minute, where the change on the internal temperature, or internal energy, this equation I just read off is what calculates that. Even though we've changed a few of the, we've had a few constants that have gone back to the other side, it still calculates what we want. And now it's calculating the change in temperature, as that's what this entire formula is dependent on.
Now that we've gone over this problem and we've derived KCA, which we knew, we derived DCA and DT, so our mass balance equation and our energy balance equation, now we can get to code this out. And so for C2, it asks us to numerically solve the initial value problem used during scipy.integrate. So we're going to be using solve IVP again, and plot your results for TC290 and TC305. And we want to explain what happens at 305, because it is quite interesting. So there's going to be a lot of switching back and forth, so get ready for it. So I imported our regular libraries. So we have Q equals 100, right? Yeah, Q equals 100. Yes, it's going to be a while. CAI equals 1. TI equals 350. Okay, let's see. Volume equals 100. Rho equals 1,000. Rho equals 1,000. C equals 0.239. C equals 0.239. Negative HR, so we're going to do neg underscore HR equals, is it 5e to the 4th? Yes, it was. E over R, so we're going to call this ER equals, oh god, it starts with a 7, right? No, 8750. So 8750 K0. Let's see. K0 equals 7.2 e to the 10 equals 7.2 e to the 10. And again, that unit is interesting. It's in reciprocal minutes. UA, or the super coefficient, equals 5 e to the 4th. And TC, or TC naught, equals 300. CA naught equals 0.5, and T0 equals 350. Oh, man. Excuse me. All right, and so it wants us to change TC. So, yeah, so it's at, right now it's at 300. And so basically what we're going to do is it says, so based on increasing the cooling by changing TC from 300 to 290, and then from 300 to 305. So I'm just going to start it at 300, code everything out, and then we're going to change it to 290, see what happens. Go back to 300, review, or not review, just make sure we remember what it looks like, and then go to 305 and see what happens, and explain that behavior there. Okay. Oh, wait, one more thing. We're going to need a time end for when we solve the IVP. So I'm going to use 10 for now, as things can get rather big real fast. So we're going to define RHS, right? And we're going to call this as a time vector. And what? Oh, I got to put that, huh? And so, as you know, we're solving for the concentration, and we're solving for, what was it again? I know we're solving for the concentration and the temperature, yeah, obviously. And so we're going to have CA, comma, T equals this vector. All right? And now we get to input our equations that we've calculated. Sorry about that. My computer just kind of blue screen of death for me there. So we're going to get right back to it. So we have KCA, or the rate that K is going to be consumed, equals CA, concentration of A, multiplied by the K0 to the power of negative ER over T. So I'm going to copy that, even though this doesn't work that way, so we're going to have to do multiply by NP dot, oh gosh, not power, it's going to be E, NP dot power. I mean, if that works, I would hope so. And now, the next thing we can do is calculate DT, or not DT, DCA. Control C. All right, so we have Control V. Let's see. I really hope this works. I mean, it looks like it should. I'm drawing a blank on, I know you just take it to the power. I'm just drawing a blank on the NP format for that right now. So what we have here is what we derived. So DCA equals the rate minus the changes in concentration divided by the volume minus KCA. So this is this makes sense, as this is the rate that's leaving. We're going in and minus the leaving, and then this is what's being reacted. So now the next bit is the fun one. So we're going to call this DT equals, let's get rid of that. So we have Q minus TI. So let's fix everything up. TC, for the temperature coolant. I put TC0, and I should just put TC. The way we're going to change it is we're just going to change that manually. and then I put negative underscore HR as that's what it is. If it's negative, it means it's exothermic, and ours is. So we put negative in the coefficient as a way to let you know that that it is exothermic, but it's positive in this term. So then we have UA, which is taking away the temperature via the coolant, which is divided by the density times volume times the specific capacity. Now we want to return two values, dCA and dt. But if you notice, we put in this order CAT, so we have to keep that order. And we want to put this in a list, so we're going to do dCA, comma, dt. And that should get us our, hey, nothing broke, our RHS, or first function. So we're going to call res, now we're going to do solve IVP, equals solve IVP. Now the function, so RHS, says function. Okay, now the time span, and so we're going to do 0 to 10, or Tn. What's next after? Now we want to do the initial conditions, so CA0 and T0. So CA0, comma, T0. And then what? Now we want to do method. So method, I was looking up methods over here, and we're going to use Radu, R-A-D-A-U. He's got a funky last name, R-A-D-A-U. And now, the last thing is we're going to be doing dense underscore output equals true. And this is just an easier way to give us our values, as it's going to be in a vector form. And let's see. Oh, okay, so it says, it's my mistake with the power. And so what we want, let's look this up. NumPy power function. Oh, it's EXP, right, for exponential? That would make sense. EXP. Let's try that. So now it's on to DT. It says float object is not callable. So let's go through this. So we have DT. Maybe if I make this an uppercase DT, that way it doesn't have any issues with maybe if we're using time as a function. So DT. I'm willing to bet that's not the issue, but we can try it. So it says float object is not callable, which means something in here is not working. So we have Q times TI. I don't see anything that's a float up here. So it's a variable. Okay, I've got rho, I've got volume, I've got C. Just go through each thing and make sure it's not a silly variable. UA, that's good. Good. Okay. Good. 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 So this is saying that DT, float object, is not callable. So I'm obviously missing something somewhere. The only thing I can think of right now is that it's going to be KCA is having that issue. All right, so there seemed to be a very small issue in the code with using spaces for some reason, and so I got it all to end up working out, but it was an interesting conundrum. So now, what we're going to be doing is creating our plots. So first we need to get our x value. So we're going to be doing x, or no, we're going to call that t plot equals linspace, np.linspace, that's better. And so we want to start 0, stop at t end, And then how many points? We want a bajillion, or sorry, 1,000. And so now, we're going to be doing res, or, so we do res.sol tplot, and that's going to be equal to, I want to say DCA and then T. So DCA, comma T, or DT. As what we're trying to do here for res.sol is it organizes the collection. So again, I feel like I'm doing something wrong, but we're going to keep moving. So now we're going to be doing fig equals make underscore subplots. We want rows equal 1, calls equal 2. And we want to do fig dot update underscore scatter. And so now, first we do y equals the, let's do DCA first. Y equals DCA, comma, x equals tplot. Let's see, what's next? We have x, we've got y, then we do name equals, we gotta do mode. Mode equals lines. Okay, now we do name equals, we're going to do CA. And lastly, we need to do row equals 1, call equals 1. And okay, I'm going to do this to see what I messed up. Object has no attribute. So maybe, I don't think it's update, I think it's add. Oh, perfect. So that's the first one before any modifications. Maybe I messed up the name, or maybe it's supposed to be over here, but because there's only one when there should be two, it's kind of mixed it up. So we're going to go and do the second one real quick. So let me get rid of that. Fig.add underscore scatter. We're going to do y equals dt, x equals tplot, mode equals lines. Let's do that. Name equals temperature, row equals 1, call equals 2. And now we can do fig.update underscore layout. Let's see. See if I can get this to work. Every time I try to do this, I somehow mix it up. So height, let's do width equals 600. HEIGHT equals 800. And then we're going to do, I think it's template equals Motley underscore dark, but yeah, okay. We're going to get rid of Motley dark and hope I didn't screw anything else up. Okay, all right. So I obviously switched these up. This should be around 800 and the height should be 600. Okay, so I'm going to make our Tn bigger so we have a bigger sample size. So we have Tn is 10. Well, let's make that 100. Oh, that should not have happened. All right, so what you can see here is on the right, our temperature starts at 350 And remember, this is our coolant temperature, which is at 300 degrees right now. So it starts off at 50. Okay, I gotta make this width bigger. This is gonna make me insane. Maybe if I make it 1,000, it'll change. Okay, that's better. Let's do 1,200. That's better. So, as you know, the rate at which the concentration at A is consumed is dependent on the temperature. As if you look up here, Ca, the rate at which this is consumed, which is Kca, is dependent on the temperature. And so, if our coolant, which is doing its job, as you can see, the temperature starts to drop. This means that the rate at which it's going to be reacting, or C is going to be reacting, is going to decrease, which means there's going to be a buildup of Ca until we get around 0.877 of like a constant fixture. And our temperature down here reaches a constant 23.4. And so that's what happens at 300. Now let's try 295 and see what happens. 295. 295, we get the same thing. But I think I was supposed to start off with 295 instead of 300 as it was shown. And so instead of here, it's at, so we lowered the coolant temperature, which means the temperature and the amount, and let's work through this. So if we lower the coolant temperature, that means the temperature here is going to be lower, which means the concentration amount, which means the rate at which it's going to be consumed is going to be lower, which again means we're going to have a higher concentration inside of our tanks, which you see here, instead of 0.85, 0.82, we have 0.92. And again, you see here, it's 317 instead of what it like 324 last time. So now, let's do 305, the magic number. And my, that is ugly. So what we're going to do is break down the Tn. We're going to make that around 10 again, so we can get nice up and close with this. Okay, so what you see here is our temperature initial. First let's look at the graphs. They're pretty ugly if you look at it. And let's break it down. So our temperature starts to skyrocket. And so what that means is that when our temperature increases like crazy, that means our concentration is going to decrease like crazy. Because a bigger temperature means a faster rate at which A is going to be consumed, which you can see here. And so you notice how these are kind of the inverse. They kind of fit like a glove in a hand if you kind of flip one over. And that's because when A has its maximum concentration after that initial very steep decline, its X value is around 2.5. And if we go over to around 2.5, it doesn't line up exactly, you can see that's when the temperature is at its lowest. It's basically what it's saying is that it's going to oscillate. And so, which, I mean, I guess you could have gotten from the question, explain the oscillatory behavior. It's because these are going to be fighting each other, which means when the temperature decreases because there's no more A to react, that means A is going to build up because the temperature has to decrease as there's nothing else to react, nothing exothermic to be released. And so it's kind of, you can think of it as a push and pull, where I'm going to be pushing the temperature over to this side, which means A has to pull all of its concentration out as it's being reacted, and then it's going to pull back. And so I'm going to make my temperature decrease as I'm pulling it back, which means the concentration has the chance to build up again. And so if you were to do this in this would be like an actual process, your customers would not be very happy, as you would not have a very uniform grade. It would be very hit and miss depending on which time your product was made. It could have a very high concentration or a very low concentration of A, which you want in said product. And so I hope that explains the oscillatory behavior at 305. And before we go back, let's just look at 300 again so we can get a general idea of what we were looking at before. In which it's a little, I'm not going to say overbearing, but you notice it reaches a point and it stays very close to said point. Where here, it's almost like, you think of it beating something down, like in a zoo. They've kind of trained it, or it's been pushed down to stay at this constant temperature, and because the temperature is so low which is as a result of the coolant temperature, our concentration gets to build up.